Every level of AI supercomputers explained. Level 1, Consumer AI. It starts small, on your desk, in your laptop fan's quiet hum, your phone's photo filter, your gaming GPU pretending to be a genius. This is the first level of AI computation, consumer AI. Every frame your GPU renders, every ChatGPT tab, every Photoshop remove background click, it's all local inference. Your graphics card becomes a miniature supercomputer for a few milliseconds at a time. Modern chips like Nvidia's RTX 4090 or Apple's M-Series Ultra can crunch trillions of operations per second, small enough to fit in a backpack, yet strong enough to generate worlds in seconds. Here, AI is personal. It powers your autocomplete, upscales your video game textures, and writes code beside you in VS Code. These consumer-grade systems run the same math as the world's largest clusters: matrix multiplications, tensor operations, floating point 16 precision, only scaled down to watts instead of megawatts. They use CUDA, Metal, or DirectML to turn raw pixels into intelligence. The entire AI revolution began here. Curious engineers overclocking GPUs not for games, but for thought. A single GeForce 8800 GTX running neural nets in 2006 was the spark that would evolve into trillion-parameter monsters decades later. And even now, the line between gaming and research hardware keeps blurring. The same silicon that renders Cyberpunk also trains diffusion models for billion-dollar startups. But consumer AI is a sandbox, fast, flexible, and limited by power. Once you need more than a desk can handle, you look upward, toward the digital cloud stacked above you, humming with rented intelligence. You can spot this level when your GPU heats up like a toaster, your fan screams, and yet your model still begs for more RAM. That's the sound of a personal machine trying to touch the stars. And above those stars waits Level 2. Level 2, AI in the cloud. Now your computer lets go. The hum of your GPU fades, replaced by the echo of data centers the size of cities. This is AI in the cloud, the second level of intelligence, where hardware stops being personal and becomes rented power. When you run ChatGPT, Stable Diffusion, or Gemini, you're not talking to your own machine anymore. You're reaching into a warehouse filled with tens of thousands of GPUs, each one stacked like silicon soldiers, crunching numbers for millions of people at once. Companies like Amazon Web Services, Microsoft Azure, and Google Cloud rent you pieces of these digital fortresses by the hour. You don't buy hardware, you borrow intelligence. Each instance spins up virtual clusters of GPUs, Nvidia A100s, H100s, or AMD's MI300XS, cooled by rivers of liquid nitrogen and powered by entire substations. Inside, AI runs at planetary scale, language models training across continents, images generating in milliseconds, voice models whispering across the globe before you blink. Your prompt doesn't go to a single computer. It travels through a labyrinth of nodes, storage pools, and accelerators, getting split, parallelized, and reconstructed before your answer even reaches the screen. But here's the catch. Power comes at a price. Cloud AI runs on demand, and every computation burns money like fuel. For big companies, renting thousands of GPUs for weeks can cost millions. Yet, it's the only way to train something at the frontier. Models with hundreds of billions of parameters, datasets stretching from human language to human behavior. Compared to Level 1, the cloud is impersonal. It doesn't care who you are. It just serves cycles. You don't hear fans or see LEDs. You just see a progress bar that feels like it's connected to the universe itself. And while anyone can rent this power, few can afford to hold it long enough to make something truly intelligent. You can spot this level when your AI project suddenly says spinning up instances or connecting to compute region. That's the moment your code stops being yours. It becomes distributed across the nervous system of the internet. This is the layer where AI becomes industrialized, where silicon turns into service. But above this digital weather, something heavier brews. When companies stop renting power and start owning it, when entire rooms are dedicated to nothing but GPUs breathing heat, that's when you cross into Level 3. Level 3, Enterprise AI servers. Now the cloud descends to Earth. You can touch it, hear it. It's humming behind locked glass doors in corporate basements, where cables run like veins, and the air smells faintly of ozone and ambition. Welcome to Level 3, Enterprise AI servers. This is where companies stop renting intelligence and start building it in-house. These are not home rigs or cloud credits. They're AI appliances designed from the ground up to think at scale. Each one is a self-contained data engine, built with the precision of a rocket and the appetite of a furnace. Take Nvidia's DGX systems, for example. A single single DGX H100 rack contains 8 of NVIDIA's most advanced GPUs, each one capable of up to 4 petaflops of AI performance. They communicate through NVLink, a high-speed fabric that moves data between GPUs faster than RAM can blink. Add in terabytes of memory, liquid cooling loops, and fiber connections, and you get a machine that can train a billion-parameter model before lunch. Or look at AMD's Instinct MI300A, a unified chip that merges CPUs and GPUs into one massive 3D stacked slab of silicon, connected by high-bandwidth HBM3 memory. It's not just a graphics processor anymore. It's an accelerated brain, designed for high-performance computing and AI side by side. Enterprises buy these machines in clusters. Banks, biotech labs, car manufacturers, every company trying to predict, simulate, or automate reality. They don't want to rely on cloud latency or external costs. They want local control, the ability to train sensitive models, handle private data, and scale intelligence directly under their own roof. Compared to Level 2, this world is grounded, physical, and proprietary. Each rack hums like a jet engine and gulps enough electricity to power a neighborhood. Technicians wear jackets because the air conditioning runs cold enough to freeze thoughts. Here, AI stops being abstract software and becomes tangible infrastructure, metal, heat, and noise translating into cognition. You can spot this level when companies start calling their servers clusters and their databases brains, when executives tour rooms full of glowing racks like art galleries. It's where AI gets expensive, heavy, and territorial. And when one company isn't enough, when a single cluster can't handle the math, multiple racks unite into one living system. This is where AI starts to evolve beyond a machine room. The temperature rises, the lights dim, and the hum becomes a roar. Welcome to Level 4. Level 4. On-prem AI clusters. At this level, artificial intelligence becomes an ecosystem. No longer a single box or rack, but a miniature city of computation, custom-wired, climate-controlled, and endlessly hungry. Welcome to on-prem AI clusters, where companies and research labs stop experimenting and start engineering empires of silicon. This is the beating heart of any serious R&D organization, where entire rooms are lined with GPU nodes connected by kilometers of fiber optic cabling. Each node houses multiple accelerators: NVIDIA H100S, AMD MI300XS, or Intel Gaudis, all orchestrated through high-speed InfiniBand networks that move data so fast it feels like thought teleportation. Thousands of cores operate as one collective organism, each node passing gradients, weights, and tensors like neurons firing across a digital cortex. Banks use clusters like these to model global markets in real time, predicting risk faster than human analysts could read a spreadsheet. Pharmaceutical labs simulate molecules by the millions, compressing months of trial work into hours. Automotive giants like Tesla and BMW feed petabytes of driving footage into their local clusters to train autonomous driving AIs under absolute secrecy. This is computation as national security asset, guarded, encrypted, and tuned to the millisecond. Unlike cloud systems that scale by renting servers, on-prem clusters are owned, maintained, and customized. Every fan speed, every power curve, every packet route is engineered for maximum throughput. They can sustain workloads 24/7 without surrendering data sovereignty, a crucial factor for industries that handle classified or proprietary information. It's why government agencies, medical research institutes, and energy corporations pour billions into private AI infrastructures. You can hear this level before you see it, a deep, resonant hum that vibrates through the floor. Liquid cooling lines snake through the racks like veins, carrying away heat that could melt aluminum. Maintenance teams wear noise-canceling headsets because the fans alone roar above 90 decibels. It's not glamorous. It's industrial intelligence, precision-built, perpetually awake. You can spot this level when AI isn't just a tool, but a facility. When data scientists work beside mechanical engineers. When the building itself has a heartbeat. Because here, computation stops being virtual. It becomes architecture. But even these engineered temples pale next to what waits above. Beyond private clusters lie national monuments of computation, supercomputers whose AI performance dwarfs everything below. They don't run in rooms, they run in hangars, and their hum shakes the earth. Next stop, Level 5. Level 5, AI-accelerated supercomputers. Now the machines stop serving companies and start serving civilization. This is Level 5, AI-accelerated supercomputers. The moment where computation transcends commercial purpose and enters scientific mythology. These aren't servers, they're synthetic planets. Massive installations built across entire halls, each the size of an airplane hangar, consuming megawatts of power just to breathe. Systems like Frontier in the United States, LUMI in Finland, or Leonardo in Italy stand as the monuments of human engineering, and every one of them has a soul made of GPUs. Inside Frontier, over 37,000 AMD Instinct accelerators work in perfect harmony, linked by the Cray Slingshot interconnect interconnect, capable of moving hundreds of terabytes per second. LUMI, meanwhile, channels clean hydroelectric energy through thousands of nodes, producing more computational output than the entire cloud infrastructure of some nations. Leonardo blends NVIDIA and Intel technologies to run AI workloads for climate modeling, medical research, and nuclear physics. These systems are the crossroads of two worlds: the traditional supercomputing built for physics and the neural networks that learn patterns from chaos. For decades, supercomputers simulated the laws of the universe. Now, with AI acceleration, they learn them. Every byte of these machines is tuned for one goal: scaling human intelligence. They train foundation models across trillions of parameters, simulate atomic interactions for new materials, and map neural activity at scales no lab could reach alone. Some of them even run reinforcement learning at world model levels, letting AIs experiment inside digital sandboxes the size of Earth itself. Unlike on-prem clusters, these supercomputers aren't built for secrecy. They're built for legacy. Each represents international collaboration, engineers, scientists, and governments pooling funds, technology, and pride into something greater than all of them. Their cooling systems recycle rivers. Their storage arrays hold more data than the early internet. Their uptime is measured in months, not hours. You can spot this level when the word computer stops feeling accurate, when maintenance crews walk miles between racks, when one machine's downtime makes headlines. This is where AI becomes infrastructure, the nervous system of human progress. But as fast as these giants are, they're still limited by physics. The next level crosses that boundary. When we finally reach Exascale, we enter a realm where 1 second of computation equals what an ordinary human brain would do in decades. Welcome to Level 6. Level 6, Exascale AI Supercomputing. Here, computation breaks the sound barrier. This is Level 6, Exascale AI Supercomputing, where machines perform a quintillion operations per second. That's a 1 followed by 18 zeros. For comparison, if every human on Earth did 1 calculation per second, it would take 4 years to match what these systems do in a blink. Exascale computing is not just faster, it's a different species of machine. It blurs the line between hardware and organism. Each node is an organ, each GPU a neuron, each interconnect a bloodstream of light. Together, they form an artificial mind big enough to simulate entire worlds. Meet El Capitan, the upcoming Exascale system at Lawrence Livermore National Laboratory, powered by AMD's MI300 AAPU-S, and expected to exceed 2 exaflops of performance. To put that in perspective, it could process the entire global internet in seconds, or train AI models with trillions of parameters simultaneously. Its design fuses CPU and GPU into one unified die, sharing memory through 3D stacked silicon so efficiently that data barely has time to exist before it's processed. Then there's Aurora at Argonne National Lab, an Intel-driven supercomputer using Gaudi AI accelerators and liquid-cooled racks optimized for deep learning. Aurora doesn't just simulate, it teaches. It's designed to train large-scale foundation models on scientific data, enabling discoveries that can't be programmed, only learned. At Exascale, physics itself becomes a challenge. The power draw is so immense that every watt, every nanosecond, every byte of transfer is meticulously orchestrated. Cooling systems use liquid metal, data pathways are measured in atoms, and AI scheduling decides how to optimize its own existence in real time. The systems begin to self-regulate, adjusting their loads like digital ecosystems managing their own weather. What separates this level from the rest is scope. These machines don't just answer questions, they model possibility. They predict nuclear fusion stability, climate dynamics, drug interactions, even planetary formation. They build universes in the time it takes us to refresh a page. You can spot this level when you realize humanity's newest discoveries no longer come from telescopes or microscopes, but from computation itself. This is AI not as a tool, but as a co-thinker. And while these systems push science to its peak, one more layer exists, a layer that blends secrecy, power, and ambition into a single global shadow network. When AI stops serving humanity and starts protecting it, or possibly governing it, you've reached Level 7, Government and Defense AI Systems. Level 7, Government plus Defense AI Systems. Now we enter the realm that doesn't make press releases. This is Level 7, Government and Defense AI Systems, where computation becomes classified. If Exascale machines like Frontier and El Capitan are monuments to human progress, this layer is their shadow, silent, invisible, and built for power rather than glory. Here, AI isn't used to recommend videos or design drugs. It's used to predict wars, simulate nuclear reactions, monitor satellites, and secure global infrastructures. We're talking about the hidden computing backbones that quietly decide energy policy, defense strategy, and even diplomacy, long before humans sign anything. At the core of this world lies the US Department of Energy's DOE network, where supercomputers like El Capitan will run simulations for the National Nuclear Security Administration, ensuring America's nuclear deterrent stays stays viable without detonating a single bomb. Each simulation models millions of atomic interactions at scales smaller than light itself. Every result is a line of code that can change the future of global balance. Meanwhile, projects under DARPA, NSA, and European Defense AI initiatives are building classified neural networks that don't just analyze data, they decide which data matters. Some of these systems are already capable of autonomous threat assessment, ingesting satellite imagery, communications traffic, cyber intrusion patterns, and generating predictions about human intent. They learn not from open datasets, but from billions of real-world signals gathered daily, signals you and I unknowingly generate. In China and Russia, similar initiatives blur the line between surveillance and simulation. AI clusters digest social data, sensor inputs, and geopolitical indicators to anticipate unrest or economic shifts before they happen. It's not paranoia, it's policy. The arms race of the next century isn't nuclear, it's computational. The hardware running these operations dwarfs even Exascale systems in secrecy. We know the names of El Capitan and Aurora, but the systems that come after them, sometimes referred to in whispers as El Capitan 2 or Project Icarus, don't appear in public documentation. They are hybrid exascale quantum networks, fusing classical GPU acceleration with emerging qubit arrays to simulate physical and informational warfare scenarios simultaneously. Power consumption, classified. Exact architecture, unknown. But one thing's certain, these are not just computers. They are national consciousness engines, built to defend, predict, and, if necessary, decide. You can spot this level by its absence. There are no benchmarks, no keynote slides, no specs, only footprints, patents filed under subsidiaries, cooling systems built in unmarked facilities, power spikes on national grids that appear without explanation. This is where AI stops being a science project and becomes an instrument of destiny. The final layer, where computation becomes control. From gaming laptops to global defense networks, the climb ends here, at the edge of intelligence itself. Because beyond level 7, we stop designing machines to serve us and start wondering whether they already do. There's a great video on the screen now, don't miss it.